Hello class. We're going to continue with chapter 4, and we're going to discuss reaction stoichiometry. Stoichiometry is the coefficients that appear in a balanced equation. So sometimes you have 1 mole of something going to 2 moles of something else, and so we need to take account of that, and that's called stoichiometry. So we are going to explain the concept of stoichiometry as it pertains to chemical reactions, use balanced chemical equations to derive stoichiometric factors relating to the amounts of reactants and products, perform stoichiometric calculations involving mass, moles, and solution molarity, which is a new term, which is concentration. We're going to address concentration in the sections 3.4, but we'll get to those after we get to this. Reaction stoichiometry. A balanced chemical equation provides a great deal of information in a very succinct format. Chemical formulas provide the identities of the reactants and products involved in the chemical change. The coefficients provide the relative numbers of these chemical species. The quantitative relationship between the amounts of reactants and products is known as the reaction's stoichiometry. The general approach to using stoichiometric relations is similar to the concept to food preparation. For example, a recipe for making 8 pancakes calls for 1 cup of pancake mix, 3/4 cup of milk, and 1 egg. This recipe can be written as an equation: 1 cup plus 3/4 cup milk plus 1 egg yields 8 pancakes. If 2 dozen pancakes are needed, the amount of ingredients must be increased proportionally according to the amounts given in the recipe. 24 pancakes, you've got 8 pancakes per recipe and 1 egg per recipe, so that tells you need 3 eggs. Balanced chemical equations are used in a similar fashion as recipes. From a balanced chemical equation, we can determine the amount of one reactant required to react with a given amount of another reactant, and the amount of one reactant needed to yield a given amount of product. The coefficients in the balanced equation are used to derive stoichiometric factors that permit computation of the desired quantity. So let's consider nitrogen plus hydrogen yields ammonia. This actually occurs on platinum. It's the Ostwald process, I believe, or the Haber. I'm taking it back. That's the Haber process, by which we make ammonia for agriculture nowadays. This equation shows that the ammonia molecules are produced from the hydrogen molecule in a 2:3 ratio. Stoichiometric factors may be derived using any amount unit. So 2 ammonia molecules to 3 hydrogen molecules is the same as 2 dozen molecules of ammonia to 3 dozen molecules of hydrogen, or 2 moles of ammonia to 3 moles of hydrogen molecules. How many moles of iodine, 2, are required to react with 0.429 moles of aluminum according to the following equation? 2 aluminum molecules plus 3 iodine 2 molecules yields 2 moles of aluminum iodine 3. You can tell if you've got this number of moles, you use 2/3 the number of moles, you use 3 halves the number of moles of aluminum in iodine. So you divide this by 2 and then multiply it by 3. So 0.43 would be 0.43 would be 0.215, and then multiply that by 3, it'd be 0.645. So we'll see. Aluminum and iodine react to produce aluminum iodide. The heat of the reaction vaporizes some of the solid iodine as a purple vapor. So the moles of aluminum and the moles of iodine are related by a stoichiometric factor. So 429 divided by 2 multiplied by 3 is 0.644 moles of iodine. The moles of, that's propane, are related to the moles of carbon dioxide released on burning it. And then the molecules of carbon dioxide are related to the moles by Avogadro's number. Okay, so that was an example. They haven't given us the balanced equation. It just came out of nowhere. But still, the important thing here is that to go from here to here, you use a stoichiometric factor from moles of what you're burning to the moles of carbon dioxide released. And to go from moles to molecules, you use Avogadro's number. So what is the mass of sodium hydroxide that would be required to produce 16 grams of the antacid milk of magnesia, which is magnesium hydroxide, by the following reaction? Well, you can see the ratio of the moles, but you've got to convert 16 grams into moles and then multiply that by 2 to get to the moles of sodium hydroxide. So the 16 grams divided by the 58.3 grams per mole converts those grams to moles, and then you multiply it by 2, and that gives you the moles of sodium hydroxide, and then you multiply it by its grams per mole of sodium hydroxide. That's how you go from moles to grams. You multiply by the molecular weight, in this case the formula weight, and you get 22 grams of sodium hydroxide. So the stoichiometric factor controls the ratio of the moles, but we operate in the laboratory with mass, and so we got to go from mass to moles, stoichiometric factor to moles, and then from moles back to mass. Similarly, if you're burning, what is this, octane, you convert from the mass of octane to the moles of octane, use the stoichiometric factor to get the moles of oxygen, and then back out the mass of oxygen that you would see consumed in the lab. So the examples we've just seen illustrate a few instances of reaction stoichiometric calculations. Numerous variations on the beginning and ending computational steps are possible depending on what particular quantities are provided in salt, volumes, solution concentrations, and so forth. All these calculations share a common essential component: the use of stoichiometric factors derived from balanced chemical equations. What I've said in the past is that the mole is the currency of chemistry. Everything has to be put into the mole, and of course stoichiometry relates one mole to the next, and then you jump back to the currency of everyday life, which is mass. Okay. The flowchart depicts the various computational steps involved in most reaction stoichiometry calculations. So you relate the volume of the substance to the mass of the substance, from the mass of the substance to the moles of the substance, or you can have a volume of solution, and using its concentration, you can get the moles of the substance. You could be talking about the number of molecules you have and using Avogadro's number to get to the moles of the substance. To jump to this one, you use the stoichiometric factors, and then you can be talking about the volume of it, the mass of it, the volume of a solution of a given concentration, or the number of particles. Airbags deploy upon impact to minimize serious injury to passengers. I guess what they're getting at here, the sodium azide, which explodes in here, gives rise to a certain volume of gas. And so they needed to know the mass of sodium azide to use in the airbags in order to produce just enough gas to fill them up. Okay, section 4.4, reaction yields. Explain the concepts of theoretical yield and limiting reagents and reactants. Derive the theoretical yield for a reaction under specific conditions. Calculate the percent yield for a reaction. You did this already in the copper lab. You derived a theoretical yield, and then you calculated the percent yield. The theoretical yield is what you would predict from the stoichiometry and the number of moles, and the percent yield is the ratio of what you actually get to what you theoretically could have gotten. And percent yields normally should be less than 100%. Okay, the relative amounts of reactants and products represented in a balanced chemical equation are often referred to as stoichiometric amounts. All the exercises in the preceding module involve stoichiometric amounts of reagents. In more realistic situations, reactants are not present in stoichiometric amounts. Actually, you usually have one reactant in higher concentration in order to drive the reaction completely to products. And so you have a little bit of one of the reactants left over. And hopefully you have something that precipitates out or is otherwise separable from the starting material. Consider making grilled cheese sandwiches. 1 slice of cheese plus 2 slices of bread equals 1 sandwich. Provided with 28 slices of bread and 11 slices of cheese, one may prepare 11 sandwiches per the provided recipe. All the provided cheese would be used and 6 slices of bread would be left over. So in this case, we're going to call the cheese the limiting reagent. The number of sandwiches prepared has been limited by the number of cheese slices. Cheese is the limiting reagent. The limiting reagent will always be entirely consumed, thus limiting the amount of product that may be generated. The bread slices have been provided in excess. Bread is the excess reagent. So, sandwich making can be illustrated with the concept of limiting and excess reagents. So here's this is your chemical reaction. 1 sandwich equals 2 slices of bread plus 1 slice of cheese. This is what you're provided with. 28 slices of bread and 11 slices of cheese. And all the cheese is used. It's the limiting reagent. And excess bread is left over. It's the excess reagent. Now, consider a chemical process. Hydrogen plus chlorine makes hydrochloric acid. Imagine combining 3 moles of hydrogen and 2 moles of chlorine. One approach for determining the limiting reactant involves comparing the amount of product expected for the complete reaction of each reactant. The reactant yielding the lesser amount of product is the limiting reagent. So 3 moles of hydrogen would produce 6 moles of hydrochloric acid, assuming it had enough of everything else to react, and 2 moles of hydrochloric acid would produce 4 moles of hydrochloric acid. So chlorine produces 4, hydrogen produces 6, therefore chlorine in this amount is the limiting reagent and hydrogen is the excess reagent. So just what I said, the hydrogen will produce 6 moles, the chlorine will produce 4 moles. The chlorine will be consumed once 4 moles of HCl are produced. Unreacted H2 will remain once this reaction is complete. Cl2 is the limiting reagent and H2 is the excess reagent. Before the reaction and after the reaction, we still have some hydrogen left over. Green being chlorine, white being hydrogen. When hydrogen and chlorine are combined in non-stoichiometric amounts, one of these reactants will limit the amount of hydrochloric acid that can be produced. The illustration shows a reaction in which hydrogen is present in excess and chlorine is the limiting reagent. I'm going to add that this is actually a preferred situation because if things are exactly in stoichiometric amounts, sometimes they take a very long time to react, and you may still not get in the laboratory time scale, you may not get 100% yield of the product. The amount of product that may be produced by a reaction as calculated per the stoichiometry of an appropriate balanced chemical equation is called the theoretical yield of the reaction. So in the reaction we just looked at, its theoretical yield is 4 hydrochloric acids because that's consistent with what the limiting reagent would produce. The amount of product obtained is called the actual yield and is often less than the theoretical yield for a number of reasons. There could be competing side reactions, there could be incomplete reaction, and it could be difficult to recover the product. The extent to which a reaction's theoretical yield is achieved is commonly expressed as its percent yield. The percent yield is the actual yield over the theoretical yield times 100%. When calculating percent yield, both yields must be expressed using the same units, so these units will cancel. So this could be in percent and this could be in percent, but the percents will cancel, and to put this in percent, you have to put 100% there. Upon a reaction of 1.274 grams of copper sulfate with excess zinc metal, 0.392 grams copper metal was obtained according to the reaction. Copper sulfate plus zinc solid gives copper solid and zinc sulfate. What is the percent yield? So the way this will proceed is that you will begin with the grams of copper sulfate, the grams of copper sulfate, and you'll divide it by the formula weight of copper sulfate in order to get moles, the currency of chemistry. And with excess zinc metal, so we're not going to be concerned with zinc. We just say we have enough. And we produce 0.392 grams of copper metal. Well, that also needs to be converted into moles. That's one way to do it. Or we could convert this completely to grams of copper metal and use that ratio. Okay, so copper sulfate divided by its formula weight gives you X number of moles. There's 1 mole of copper per 1 mole of copper sulfate, so that's your stoichiometry, times 63.55 grams of copper per 1 mole, and that gives 0.5072 grams of copper. So we've got almost 0.4 divided by 0.5. It's going to be about 80% yield. So that divided by that is 77.3%. Ibuprofen is a popular non-prescription pain medication commonly sold as 200 milligram tablets. The BHC process for synthesizing ibuprofen requires only 3 steps and exhibits an impressive atom economy. Let's see. Trying to think of the name. Okay, excellent. And one more thing. Describe the fundamental aspects of titration and gravimetric analysis. Okay, that's all we're going to do for right now. Thank you very much for listening. Bye.